So there we go. And I'm gonna take a look at the YouTube side. Once it is started, I'm gonna turn it off or get out of that window. Okay, it has started. I'm gonna exit that particular browser. Oh, okay. I was just reading a direct message from one of the classmates in this class. Alright, we got about 50 seconds. And I'm going to do one last check and see how many people have turned in the negative exponent assignment. Or rather, how many people are missing. 3, 4, 5, 6, 7, 8. So we got 8 people, so 3 people turned in within the last 5 minutes or so. Okay, just in time, just in time. Not a problem. Alright, so 10 more seconds to go. So we have a choice here. We got a few choices. If you guys want to look at the solution of the negative exponent assignment, we can do that at the beginning of this class. So we could definitely do that. So just want to see. Oh, okay. So we got people saying yes. All right. So let's do that. So the lecture has officially started at this point. Okay. All right, so we got a whole bunch of yes, so we'll go ahead and take a look. And I'm going to do it using online GDB, just because it is a very convenient interface to do my programming. I don't need to. I mean, the only negative thing, is I don't get to use VI as my editor, but that's not really that bad of a deal. I mean, so I'm not going to complain too much. All right, so here we have EXP10 to EXP2 as a subroutine, and for this part, okay, what is due today is really just to handle the cases when EXP10 is negative to begin with. So what we want to do is to set up a loop and say if EXP10 continues to be negative, we stay in the loop. And obviously I have to double check to make sure that the name of this member is indeed correct. So that is defined right here. So we got EXP10, EXP2, and also Mantisa. Those are the names of the members within the structure. And now we can go in here and we then ask, are we going to do that? So the idea is you want to be able to increment EXP10, one by one until it becomes 0. So, and the way to do it is to divide the Mantisa by 10. But we don't want to divide the Mantisa by 10 until the Mantisa is maxed out. So I'm going to put some comments here. So I'm going to say the first thing we want to do is to max out the Mantisa. Yes, it is not very technical, but it captures what I need to do. And now we can increment EXP10, and we also want to divide the Mantisa by 10. And that's kind of what I want to do from the outer loops perspective. Now, there are certain things that's missing right now, but that's okay. I'm going to focus on what is important. That's okay. It doesn't have to be the most efficient, Terrence. The point is, I just want you guys to get it done. It doesn't have to be the most efficient way to do it. I mean, there are many, many ways to do this. This is just one of many ways. All right. So now to max it out, we can say while not maxed out, and then we are inside the loop to max it out. We are just gonna double the Mantisa for every iteration. So that can be done by pn points to Mantisa times equals to 2. There are many ways to do this. You can do a left shift, that will accomplish the same thing. So a left shift operation looks like this, and we just want to left shift by 1 bit. But multiply by 2 works too. You can also plus equal to itself. Those are all different ways to do exactly the same thing. So whatever you do here, we just want to double it. So now we have to go back here and ask the question. So what does it mean when it is not maxed out? So let's go ahead and replace this with the actual code. So we want the mantissa to have enough room to be doubled, and we also know that we are going to add 5 first before we um, divide it by 10. So we want to make sure that that plus 5 is not going to bump mantissa over the maximum either. So we want it to multiply by 2, and then after that we also want to make sure that we can add 5 to it. So times 2 plus 5. So on the other side we want it to be less than u and 64 underscore max, which is really just a macro defined in standard integer.h. This I talked about already. I basically gave you guys the solution of this part already. Okay, but in my head, I'm just kind of re-deriving the whole thing. So I need to do a subtract 5 first, and then do a division by 2, because the once we get out, the other operation is in the opposite order. So this is what we need to compare the mantissa to, and as long as it is okay. Well, that means, so what Ethan is describing is if you keep multiplying mantissa by 2, eventually it becomes 0, because you'll be shifting all the bits on the left-hand side of the 64-bit number, and you'll end up with just 0. So that means the comparison or the condition to get out of the loop was not set up correctly if mantissa becomes 0. Okay, so Jonathan is confused by the subtract 5 then divided by 2. Let me see. So we have to reverse the operation. Okay, let me do it like this first. Okay, so we'll handle this part, which is dividing the mantissa by 10. So this part is Pn mantissa equals to. Now we want to do the rounding thing, so that means we have to perform the mantissa plus 5 first. So so Jonathan is correct. I need to reverse the operation, which is a division by 2 first, followed by a minus 5 here, because the plus 5 is done first here. So that means we have to perform that first. And then we want to divide it by 10. Right, so we want to divide this by 10, and we don't have to use a floor because it is automatically taking the floor. This is an integer division, so it's automatically using the floor. So so I was incorrect earlier that I do a division by 5 first. I mean subtraction by 5 first, because I have to because the plus 5 is done first here. So when we reverse operations, this has to do with finding the inverse function of other functions. So if you have 2 composite functions, then the inverse function is going to be the inverse functions of those 2, but applied in the reverse order. So that's kind of a math thing. But we also want to increment exp10, which is Pn points to exp10 plus plus, or plus plus that, either way works. And we got some traffic in the text channel. If we got the same answer, we are not going to use the floor. Nobody should use the floor. So there we go. Yep. So I'm just looking at the text channel thing, and that's basically the same thing. All right. So we want it to be less than or equal to, because when it does equal to, we're still okay. We still have room to perform another doubling. All right. So I think we're good there. Okay. All right. So that should take care of the most cases. But in the assignment, I also said that the mantissa needs to have bit 63 set. Okay, so that means we're going to need an outside loop here that says if Pn points to mantissa is less than. I mean, there are multiple ways to do this, but I can just, go ahead and use this particular method. If it is less than uint 64 underscore max divided by 2, and we can use less than or equal to, because uint 64 underscore max is automatically an odd number, so we automatically have the extra room for the doubling. So now we say Pn points to mantissa, and we just want to multiply by 2 until it is no longer less than or equal to this amount. Then we know that bit 64 is set already in that case. All right. That's interesting. I cannot hear Ian. Huh. So it must be my setting here that is not done correctly. Let me fix that first, because in case you guys want to talk to me using the voice, I am gonna change it back to the default here. There we go. So now I can hear you guys too. Okay, I did not even realize that that was not turned on until I saw the message and go like, oh, okay. All right. All right, so that's good. All right, so now it's time to test the program, right? How do we test the program? There are several ways to do it, and we are going to assume that the code is working. So I'm going to put a breakpoint all the way at the end of the function, and then make sure it's a C program, and then go to debug, and there we go. And then we'll run it, R, and then with the dash n, and we'll try something like 2.34 e negative 100. Press the enter key, and it got to the breakpoint. Let's see. Yep, it got to the breakpoint. Normally, I should see an indicator. Well, the indicator that we got to a breakpoint is we see this kind of gray bar with a green thin line surrounding it. That's the indicator that we are now at a breakpoint. So now the question is, how do we know the answer is correct? Okay, it's because we can now say print pn, and Pn has the sign being 0 because it is a non-negative quantity. So we don't have to do a single thing about sign. Once it's parsed correctly from, that's using my code, it's going to be okay. This is the mantissa, and the exponent of 10 is 0, and then exp2 is 0. That is not right, right? So I forgot something. All right, so what I forgot was when I double the mantissa, I forgot to adjust exp2, because every time I double the mantissa, I need to decrement from the exp2, from the exponent of 2. I forgot to do that. Okay, so fine. Save the program again, and let's go to debug. There we go. Yep. So you guys caught it too. Very good. Good job. So now we run it again with a dash n, and the number 2.34 e negative 100, negative 100, like that. Press the enter key, and then we can print star pn, and now we got something that looks a little bit more correct. So we got a mantissa that's pretty large, okay, and then an exp10 that is 0, and an exp2 that is a negative 391. So the question is, how do we know this is right? Okay, it looks right, right? Having a pretty large mantissa seems to be what we should be expecting, but is the most significant bit set in this particular mantissa? That's one question. And two, are we going to reconstitute the original value, which is, what was it, 2.34 times 10 to the power of negative 100? So those are the questions that we would want to answer. To answer those questions, I'm going to bring out the big gun, which is a spreadsheet. So you will see that in this class we use spreadsheets a lot, okay, especially later on when we get to actual assembly language programming. We're going to use a spreadsheet a whole lot. So what I'll do is I'm going to copy the numbers into the spreadsheet first. Okay. Oh, no, that's not what I want to do. Okay, let me try that one more time. Control C, and over here Control V. Nope, it doesn't quite get just the number. What is going on? Right click and then copy. Okay, that should copy it, right? And then paste on the other side. Okay, that works. And then the exp2 is negative 391. I can just type that here. Negative 391. Alright, so now we want to see, because exp10 is now 0, so I don't have to copy that. So now I want to know what value is being represented when the mantissa is this amount and the exponent of 2 is this amount. So to calculate that, I just have to say, let's take this cell and multiply it by 2 to the power of whatever is in this particular cell. Press the enter key, and we did not get the answer back. We got something that has a e negative 99, but not really what we started out with, which is 2.34. I forgot to do something, but what did I forget to do? The loop condition is the other way around. It should be like this, not the other way, because what we are doing here is we're adding 5 first. So we are adding 5, so we have to make sure that we have room to add that 5. So exp2 is decremented correctly. I got the right order of magnitude. It's just that I did not quite get 2.34. So it looks like a biased problem to me. Needs. Oh, right. Okay, this one here. I forgot to adjust exp2. Thank you. Alright, so let's go ahead and fix that. Because every time we adjust the mantissa, we have to remember to adjust the exponent. So there we go. Forgot to do the decrement over here. Save it again, and let's go ahead and debug. So it's always important to double check your answer, right? Just to make sure that you don't make a mistake like I did here. Alright, so the breakpoint is still here, and we are ready to run it. Run -n 2.34 e negative 100. We got to the breakpoint, and this time the mantissa is the same, but the exponent of 2 is changed just a little bit, right? So it's negative 394. So we'll go ahead and change the the exponent of 2 to 394, and now we got 2.34 times 10 to the power of negative 100. Very good. All right. So are we doing okay so far here? This program is, according to this particular test case, it is working. Oh, I forgot to do one thing. Is the most significant bit set in this case? So to test that, there are several ways to do it too. So you can always test it and test it against 2 to the power of 63. So we can say, let's compute power to 63. And as long as this value is greater than or equal to this value, we are good. So this is telling me that the most significant bit, or bit 63, is indeed a 1. All right, so Colton is quoting. Yeah, so I got it wrong in my notes too. It doesn't make too much of a difference, but yes, I did make a mistake in my notes. It was reversed. It will still work for the most part. It's just there might be some really awkward boundary conditions in which it makes a difference. For the most part, it does not. All right. So are we doing okay with the solution to the homework assignment? To the first one, the one that is due today? Yeah, Colton, either way is fine. Okay, it doesn't make that much of a difference, because when you look at UN64 underscore max, it is basically 1 8 followed by, let's see, 18 zeros. So whether you divide it by 2 first and then subtract the 5, or subtract the 5 first and divide it by 2, it doesn't make that much of a difference. So it's going to be okay. It's just that sometimes I make a mistake, and other times I fix the mistake. So I'm going to fix the notes because it is the notes is incorrect in that case. All right. Well, computer science is a subfield of math, so you probably want to get used to it. Oh, either way, it doesn't make a big difference. Well, it doesn't make a big difference. It does make a difference, yeah, but not in most cases. All right. Alrighty. Uh-huh. Okay. All right. So, are we ready to go? I mean, we can actually look at the difference between those two constants. I mean, just I'm not sure whether we can get to u and 64 underscore max in the debugger. Now, if you do this in the spreadsheet, it will basically not, it won't show up with a difference at all. So if you want to find what the difference is, you're going to have to do it through the debugger. And just by looking at the thing, I think the difference is about 2. So the net difference between doing it the way where I have it here, oops, that I have it here, division by 2 first, and then a subtract 5, versus a subtract 5 and then a division by 2, the difference is 2, and it's 2 out of 18 followed by 18 zeros. So that's why it does make a difference, but the chances of you stepping on that difference is going to be very small. There is a chance that it is going to make a big difference. So this is correct. My notes is wrong. So that is that. All right. And this is not, by the way, this is not the only control structure that you can use. I have seen people using a single while loop, and inside the while loop they use a conditional statement. That would also work. It's just a little bit awkward to do it that way. So basically, yeah, so I'm not going to get into that one, but I have seen some really strange but original and creative control structure to implement exactly the same logic. And then Ashton asks, why did we need to continue to double the number after EXP10 is 0? Because the assignments asked for it. The assignment said the Mantissa needs to have bit 63 being a 1. So you have to bump it up until it uses up all 64 bits. That's part of the assignment. It's part of the description in the assignment. So there's that. That's why. All right. So with this out of the way, I think we are ready to go back to our SR latch, unless there are additional questions about the negative exponent assignment. All right, let's go back to the what we did on Tuesday. So let me go back to the tablet. So what we did on Tuesday was something that looks like this. Let me put the entire thing back into the area that is being recorded and streamed. So this was what we did on Tuesday, and we performed a sequence of operations where we had initial values of x and y being 0 and 0, and then we decided to change x first. So x got changed from 0 to 1, and this is the corresponding output, okay, you're based on the input, and then we change both inputs to 1s, and then we end up with the output being 0 and 1 over here. So what we'll do today is to change one step of the sequence. So we're going to redo the whole thing, okay? So let me redraw the whole picture. So we got x, y as our input pins, we got a, b as our output pins, and then we have 2 NAND gates, and x goes to the first input of the first NAND gate, and I cannot remember. Oops, I cannot remember how I named the NAND gates. So let me go back and check out. It's N and M. Okay, there we go. So we got this N, and we got this M over here. So Y goes to the second input of M, and then the output of N just goes to the output pin. The output of M goes to the output pin of B. And the fun part is we have a feedback mechanism. So the output of M is also going to the second input of N, and then the output of N is also going to the first input of M. So that's the circuitry. And now we want to find out, what's going to happen, if the sequence of changing the bits is a little bit different. So we're going to redo the 0, 0 first, okay? Because I want to show you how we monitor the change, or how we monitor the propagation of changes. So now we have x being 0, y being 0, and both of these are new to this circuit. And as a result, we want to find out what are they going to change. So this is going to change n dot in 0 and make it a 0. This one is going to change m dot in 1. So that is also going to become a 0. Okay, well that's instantaneous. It doesn't take any time for this to happen because it is just using a conductor to connect to those specific input pins. So now we want to see if we can determine the output of the NAND gates, which is N and M. And last time we already used a truth table to verify that if at least one input of a NAND gate is a 0, then the output of the NAND gate is going to be a 1. Okay, alright. So that means after a certain amount of time, so I'm going to put a delta t here to indicate that there is a little bit of lag time in between. So after a little bit of lag time, n dot out is going to become a 1, and then m dot out would also become a 1. And having no lag time whatsoever, this is going to cause A to be a 1. This is going to cause B to be a 1 too. So that part we kind of know. However, we also want to see, but wait, hold on a second here, because the output of N is going to M, one of the input pins of M, and vice versa. So now we go like, okay, so after a delta t, well, nope, with no delta t. So let me change it back. There we go. All right, so this is a 1. At the same time, it also changes n dot in. Oops, I take it back too. This is supposed to change m. All right, so m dot in, let's see, 0 is also going to be a 1. And then in this case, because when we change the output of m, it's also going to change the one of the inputs, the second input of n, to also become a 1. So there's no delta t in this case because the change is because of the conductor. And let me take a look at the text here. Okay, I guess we can go back to the example and use a different test case, but for now we're gonna continue with the NAND gate. All right, so now we look at this, because whenever you change the input of a gate, you have to look at the effect of that. So after a certain delta t, the output is going to be affected by the change of the input, except in this case it doesn't make a difference because x is still a 0, which means n continues to output a 1, and y is still a 0, which also means m continues to output a 1. So we will say n dot out continues to be a 1, m dot out continues to be a 1, and as a result there are no further changes because now we have reached a steady state, which basically means there are no additional changes at this point. Are there any questions about this particular analysis of the circuit to come to the conclusion that when you change both inputs of this particular circuitry, this one over here, the output, when both inputs are zeros, the outputs are guaranteed to be ones? This is what we did on Tuesday. So assuming there are no questions, now we're going to change it so last time we changed x to become a 1 first, and this time we're going to change y to become a 1 first. Okay, so to do that, we are going to, let me do this. Let me copy the entire circuitry to the next page, and then we'll do the analysis on the next page. So we'll copy this whole thing and paste it onto the next page. So now we'll continue, and this time we're going to change y first. So we're going to change y, and I'm going to put a little cross here on y, and then put a 1 over here, which means this is the change. So y becoming a 1 is the initial change. Now we need to know how is that change going to propagate throughout the circuit, and how is it going to affect all of the components as well as the output of the circuitry. So y being a 1 will take no time whatsoever to change the second input of m. So now m dot in square bracket 1 is going to become a 1 instead of a 0, because it was a 0 before. Now it is a 1. What is important now is to understand, what about the first input pin of m? It is continuing to get a 1 from n. So we have to retain all of those values from the previous analysis. In the previous analysis, there's a 1 here, and there's also a 1 here. And there's a 0, there's a 1 going here, there was a 1 going here, and this is a 0, and this was a 0, except now it becomes a 1. So this is important, because now we know that for the NAND gate M, we have both inputs being 1s. So that means after delta t, because once you change the input of a gate, it takes a little bit of time, a propagational delay, in order to change the output. But now the output of M is going to be a 0, because both inputs are 1s. Okay, let me pause here, make sure everybody understand why the NAND gate M is going to output a 0 at this point. Are we good so far? I mean, we did this analysis on Tuesday, except this happened to N instead of M. Okay, very good. So this will instantaneously change B. So B, instead of output a 1, it's going to output a 0 at this point. This is no longer 1. This is going to be a 0 at this point. So you look at this change and go like, is it going to change anything down the stream? And the question is, this node is now changed, and you can see how it is changing this 1 to a 0. In other words, N, the second input of N is also being changed from a 1 to a 0. Now I know most of you already know that, but X is still a 0. That means your N is going to continue to output a 1. Yes, that is the case. Okay, but that's only because you understand that N is a NAND gate. So if we pretend that we don't know what type of gate N is, it is still experiencing a change of its input pins, so we should still go through the analysis. Okay, so let me finish this part here, because it doesn't take any time for all of these changes to occur at the same time, because they're all connected to the same node. So now we can say N dot in bracket 1 is also going to become a 0. So that in return, after delta t, is going to change M dot out to become a 1, which it is already a 1, but we want to say that after a certain amount of time, N dot out continues to be a 1 despite the change of the input pins of N. Okay, that is really important. So we can say because both inputs in this case are zeros. Okay, so that means A continues to have a value of 1. And at this point, we can stop, okay? Because even though we just figure out, at the output of n is continuing to be a 1, but it was a 1 to begin with. So that means it's not going to cause anything else to change, because that is it's basically a dead end. It is not changing anything because it kept its old value. Are we still good so far? All right. All right. So at this point, we are going to copy the circuit again onto the third page, because now we want both inputs to be 1s. So we're going to copy this and paste it over here. And then this time we want both input pins to be 1s. And Y is already a 1, so we are not going to change the input pin Y. We are only going to change the input pin X. So now we say X is now a 1. So that means we have an immediate change over here. That becomes a 1. All right, so that is going to impact the first input of n directly. So n dot in bracket 0 is also going to be a 1. It doesn't take any time, so I'm lumping these changes into one single collection. But it is still nonetheless a change to one of the inputs of n. So that means we have to now say, after a certain propagational delay, we want to figure out what n is going to output. But in this case, because the second input of n is still a 0, which is coming from the output of m, so that means n dot out continues to be a 1, because n dot in bracket 1 is a 0. So at this point, we can stop our propagation. There's no additional things we need to track, and because this is not a change from what it used to be. It was a 1 before, and it is still continuing to be a 1, so there are no additional changes that we need to propagate to analyze. So we can write all this out, okay? M dot in 0 is a 1, but it was a 1 already in the past, from the previous slide, so it is not experiencing any change. So if the input pins to a gate is not changed, then the output of that gate is not going to change, and there's no further analysis needed at this point. All right, so are we okay with this analysis, which is basically the same as what we did on Tuesday, except it's a mirror image. Instead of looking at the bottom half of the circuitry, we're now looking at the top half of the circuitry. In other words, we're taking a vertical mirror image of what we did on Tuesday. All right, so that is good. Okay, Jason is still typing. I'm gonna wait a little bit. But this is strange, okay? Because it is really strange, because if you look at the sequence, okay, we are on Tuesday, okay, so I'm gonna write Tuesday over here. And I'm gonna need to put my tablet down because I was holding it using my hand, and it's kind of tiring. So on Tuesday, what we did was, in terms of x, y, and AB, we originally set everything to 0 as far as the input pins are concerned, and then as a result, A and B were both they both became 1, and then we changed x to 1 first. And as a result of that, output A becomes a 0, where output B continues to be a 1. And then we changed both to be 1s, and AB did not change at all. So we maintained the outputs of 0 and 1. That was what we did on Tuesday. What we did today, on Thursday, was something similar, but with a mirror image, right? So we still started out with 0, 0 as our input pins. And the output pins, definitely became both 1s. But this time we changed Y from a 0 to a 1 first. So X continued to be a 0, Y was changed from 0 to 1. And as a result, A continues to output a 1, but B was changed to a 0. And when we change X also to become a 1, now we have both inputs being a 1. then we are just maintaining the output. A continues to output 1, B continues to output 0. So when you look at these two sequences, this is new to us because in the past, whenever we do something about the input, the output would change accordingly. Okay, it doesn't matter what order we use to change the inputs. That would be true for the adders. Okay, it's not just the carry ripple adder. It also applies to the carry look ahead adder. It applies to the subtractor. Okay, all the circuitry before did not have something like this. Okay, but this time we got something that's really strange, because if you just focus on the state when both inputs are 1s, then you are going to say, just knowing xy are 1 doesn't tell me much about AB, because it's a memory device. When x and y are both 1s, we are telling the circuitry to say maintain current state. That is what it's doing. Okay? When one of the input is a 0 and the other one is a 1, we are telling the circuitry to change state, to change to a particular state. But when both inputs are 1s, we're telling the circuitry just to maintain the current state. So that is why this little circuitry here, okay, with two NAND gates, two input pins, two output pins like that, and having the feedback. Okay, this is the interesting part about this circuitry, is it has a feedback mechanism. This is called a SR latch, and it is the smallest unit of memory in your computer. And you look at this and go like, that doesn't even sound like memory, because when we want to store something, we just want to change the content to something. This one doesn't even look like it, and you would be correct. Okay, this one does not look like a memory for one single bit, for one single binary digit. So there's a way to modify it so that it becomes more like a memory unit. Okay, and that is in our notes. Okay, so the next item that we're going to look at is let me take a look. D flip-flop. And where's the notes? There we go. Click on it. So we are now done with the SR latch. The next item is called a D flip-flop. Okay, so here's a D flip-flop, and you're gonna say, but where's the picture? Where's the circuit diagram? So this is my attempt of introducing a different way to represent a circuit. So instead of representing a circuit in a graphical way, I am now representing a circuit by looking at the logical connection between the components. You hate it already. Very good. Because if anyone is transferring to UC Berkeley, this is what you're going to do for your final project in the computer science undergraduate program. And you're going to use notations like this, not exactly, being exactly the same like this, but you're going to use notation like this to describe a complex circuit. You're going to look at a processor design, and it's going to be expressed sort of like this. In this class we are going to use we are continuing to use Logisim. Don't worry, we are going to continue to use Logisim. But in industry, they don't do it like this. They don't use Logisim to design a complex processor like the AMD or the Intel processor. It's kind of like, Logisim is like flowcharts, okay? And this is more like C and C++ programming. So let me ask you this question: why don't we use flowchart to program? Why do we use C or C++, in industry for programming instead of using a graphical programming language? And there are graphical programming languages. Scratch is one, okay? So why don't we use your graphical quote unquote language to write complex programs? Can someone tell me? So we got a few takers. Very good. I like it when you guys are actively thinking and answering questions or fixing my bugs. I like that too. Too much memory use? Nah, not really. I mean, the computer can handle all that. The question is, I know, but I'm not going to say. Okay. Yes, I trust you. It's because, okay, so, but nobody has actually pointed out the reason yet, okay? Because graphical programming doesn't solve huge set of problems. It does. I mean, it has the same expressive power. It can express algorithms exactly the same, with the same. Okay, whatever you can express using a programming language like a conventional programming language, you can express it using a flowchart or a graphical programming language too. The difference is, no, it has nothing to do with GPU. Okay, I like the term professional, but why is it more professional to program in a text language instead of a graphical language? All right, so I'm going to give you the answer. Okay, when you program in a graphical language, think about when you need to insert something. The placement of the items, okay, if you want to make a subroutine larger, you're going to have to physically, not physically, but in the two-dimensional plane, you're going to have to move things around to make the space, right? And it is also very not, it's the opposite of concise. Okay, it's very verbose because you're going to see all the arrows flying around, and basically the density of your code is going to decrease significantly. It can still express the same thing. You can still express loops, you can still express conditional statements, you can still express even throwing exceptions, and so on and so forth. Yeah, that looks good in a movie, but I challenge you guys to use Scratch to do your homework assignments for CISP 430. Okay, let me describe to you what Scratch is. I know I'm digressing, but I'm making a point that is kind of important. So this is MIT Scratch. Okay, it is a great way to get into programming. If you know someone who is like 6 years old and you go like, hey, I think you should probably get into programming a little bit, Scratch is great for that. It's impossible to have syntax errors because it's all drag and drop, and it has something like YouTube, so all the feature projects you can actually, you can get to the source code, and they have some games and stuff like that. It's a really cool programming language. Trust me, it is really fun to do. However, if you want to do anything that's complex, it's not like it cannot be done. It's just that it's going to be huge. Okay, it's going to take up a lot of screen space. It's not going to be easy to edit or to analyze. That is the problem. Okay. It doesn't have pointers, but if I last time I checked, I think it does have the concept of references. But it's really kind of cool. Oh god, Scratch. Oh no. It does have some really cool features. If I remember correctly, it has signal and wait, which are very advanced concepts to synchronize threads. So it does have some pretty cool features. But when it comes to the ability to express complex algorithms, it is not the best way to do it because you're going to end up with like a gigantic, um, you know, picture, just to represent some simple logic, and that is the problem. So that gets us back to where we were over here. Because when you need to express complex circuitry like the AMD or the Intel processor, or even just one of the GPUs, of your one of the cores of your GPU, that's not going to be simple. Okay, you can use Logisim to express it. It's not going to be fun to do it. So instead of doing it that way, it is much better to use a text form to do it. Okay, now in industry there are two languages for that purpose. It's time to take row, so I'm going to take row first, and then we'll get back to this discussion. Let me show you the question first, and then we'll get to the answer. Alright, so the answer to today's row taking activity is clocked. So hopefully we can get to clocked circuitry at least a little bit, because that was the intention. So there you go. Let me click save and publish. So you have 9 minutes to enter that word clocked. And Nicholas is correct. It is cool until you have to work on anything, a large project. Exactly. And a lot of people think about in the movies, having all of these, virtual thing, they just kind of do the hand gesture thing, this and that is really cool. If you have to operate a computer like this for the whole day, you're gonna have injury, like on day one, because your hand is not rested. You're basically just, doing this all day long. Just try to do this for half an hour and see what happens. Um, I noticed that in Minority Report, because in Minority Report, the character played by Tom Cruise was using a user interface just like that. Okay, you just kind of drag things around in air. So when your arm and your palm is not resting on the surface, you can do it for a few minutes. It looks cool. It feels kind of fun. After an hour, your arms and your hand will be sore. Wrist training. Oh, in this case, it's not going to be carpal tunnel. It's going to be muscle sore. It's just by having to hold your hand, in midair like this, for the whole time. Yep. The snap. The snap. Alrighty. So I'm gonna assume most of you are done with the road taking activity, and now we are moving back to this thing here, and we'll find out what it is, right? So I'm borrowing, the convention from C++ programming. So anything that starts with the uppercase is the name of a class, and I'm just declaring an object, with that class. Now, circuit is lowercase. It is basically an object already in existence, and we're using the method add node to connect various pins of these components together. Okay. So I know you guys are kind of looking at this and go like, what is the circuit? What does it look like? Let me go ahead and draw this using the tablet so we can all see what it is supposed to look like. And I just got past the tablet screen. There we go. Alright, so we are going to put the circuitry maybe around here. And then I'll just go ahead and draw it by hand. Alright. So, we have input pins and we have output pins. So we got two input pins. One is called D, the other one is called EN. And then we have two output pins. One is called Q and the other one is called NQ. Alright, so I just have to be careful not to get out of the area that is being recorded. So we got D, and then we got EN, like that. And let's see, what other components do we have? We got two output pins. So let me put the two output pins all the way to the right hand side where you can still see. And the output pins are called Q and NQ. Alright, so output pin one is here. We'll call this one Q, and the other one is NQ. We'll put it over here, like so. Oh, okay, never mind. I already moved things a little bit too far to the right, so you cannot see it. There we go. Okay, that's probably okay. Alright, so what else do we have? We have two NAND gates, okay? One is N1 and the other one is N2. We have a SR latch, which is called SR, and then we have a negation gate called N. Alright, so now let me just put all those items in here. But before I do that, I want to kind of take a quick look at the circuitry so that things do not look too bad and out of hand. So I'm going to put my SR latch over here. Okay, so with the SR latch, it has got two inputs and two outputs all by itself. The SR latch has one input called S, one input called R, and one output called Q, and one output called NQ. And this is our SR latch, which is also called SR itself, lowercase. And then after that, we got the NAND gates. Okay, so we're gonna have the two NAND gates. We'll put the two NAND gates over here. One is here and one is here. And then we have one NOT gate N, and the NOT gate N is only used to connect to N2.in1, so it kind of makes sense to put it here. So this is our NOT gate. All right, so now we got all the components. Now the question is, how are they connected? Let's deal with the easier one first, okay? So the easy ones would be something like this, okay? N1.out connects to SR.S. So let's call this one N1, let's call this N2, and this one is N right here. So N1.out, which is here, goes to SR.S, which is right here, and N2.out goes to SR.R, like that. And let me check the Discord because one of my screen is covering the Discord screen, so I have to double check, make sure that I'm not missing a whole lot of text here. All right. All right, nothing too important in our discussion. This is the reason why I have a off-topic channel for all of those conversations to go. But sometimes I'm the instigator, so I am guilty of that too. Anyway, so there are a few other ones that are also easy, such as sr.q goes to q, and then sr.nq goes to nq. So those two are pretty easy too, just like that. All right, so now let's work with something that is a little bit more complex. So D as an input pin goes to the first input of N1. It also goes to the input of N, which is just a NOT gate. So now we hook up D to the first input of N1, but it also goes to the negation gate here. And then En goes to the second input of N1, and it goes to the first input of N2. So En, which is this one here, it goes to the second input of N1, which is right here, and it also goes to the first input of N2. So we will tap here and then hook it all the way to here. And then we got N. So N.out is going to the second input of N2. So it goes from here to here. There we go. That wasn't too bad, was it? Now, there's a reason why this type of notation is handy, and it kind of goes hand in hand with that crazy formula that we have mentioned in carry look ahead. All right, so you have all done the carry look ahead for 3x3 adder, and some of you are thinking, oh, that thing for K3, that's crazy. I mean, that's a lot of wires, a lot of gates already. Just kind of imagine you have to work with, let's say, K16. What do you think K16 is going to look like? It's going to look a little bit cumbersome, okay, to say the least. Do you want to do it by hand? Probably not. So if you have notations like this, you can now set up a loop. Remember, I showed you guys, how I can use a loop to generate the expression out of that formula when we talked about carry look ahead. So imagine that is not generating the expression, and instead it is generating these add node, and also it's generating the necessary gates and also the necessary pins. So now you can use an algorithm, you can use a program to generate a complex circuit where the logic is not too complex, but the outcome is really cumbersome. So now you can use logic to do it instead of having to rely on your Logisim Kung Fu to do it, okay? Because that's just not going to be a very efficient use of your time. So all of these things are kind of related. And for those of you who are planning to transfer to the computer science program in Berkeley, and I suspect several UCs would also have similar projects, they use what we call HDLs in order to describe a circuit. So in HDL, no, not the cholesterol thing. Hardware description language. Hardware description language. There we go. So there are two main hardware description languages. One is called VHDL and the other one is called Verilog. I cannot remember which one Berkeley was using. They could have switched between these two. Industry tends to prefer Verilog, and then universities tend to prefer VHDL. Verilog looks a little bit like C programs, except you're not really specifying the program to execute by itself. You're using your C-like code to describe how to generate a circuit. That's what Verilog is for. Well, one of the purposes. And VHDL is very similar in terms of what it can do, except the syntax is different. So these two are used in industry a lot in order to describe a circuit. So instead of using Logisim and instead of using what we are doing in this class, basically using the pictorial representation, it's all going to be in text representation when you get to more advanced designs. So I just want to throw this out, okay, because some of you may be going for a computer science degree in Berkeley or in one of the UCs where they use a language, okay, in text to describe a circuit. So by the time you get there, at least you understand why it is like that and approximately how to use it. I mean, it's definitely not this syntax here. This is like C++ syntax to try to do the same thing. Alrighty, so now that the circuitry is done, let's go ahead and analyze what it is going to do. So over here we have the circuitry, and I can move it over here so that, because there's no need to look at the text for now, so I'm going to use the entire picture. The picture is going to take up the entire space. Alright, so now the question is, how does this work? Okay. So en is enable, okay, and when enable is a 0, we maintain the state of the SR latch. That's the idea. When en is a 1, it is enabled, then D is going to be mirrored by Q. Let me say that one more time. When en is a 0, we basically want to disconnect D from the SR latch. So the SR latch will basically maintain whatever state it is in. Now, when I refer to the state of a SR latch, I'm referring to the output Q and the output of NQ. So when en is a 0, I want the SR latch to maintain its current state. Q and NQ should not be affected by the D pin at all. On the other hand, when en is a 1, when the circuitry is enabled, I want the Q pin of the SR latch to mirror the state of the input pin D. That is the purpose of this circuitry here. And Daniel said, when en is a 0, the SR latch will retain whatever state it is in. That's exactly what I was trying to say. Yes, very good. So the question is, how does it get the job done, right? So the first thing we want to do is to analyze what happens when en is a 0. Okay, so we'll say en is a 0 here. And that 0 is going to go to a few pins. So I'm going to say en equals to 0. We basically mean n1 dot n1 bracket. Oops. Okay, let me use the correct syntax here. n1 dot in bracket 2 would also equal to 0 because it is connected directly from en. And the same thing with n2 dot in bracket 0. Oops. Never mind. Wrong index here, index 1. There we go. So these are all going to be zeros, right? Because they belong to the same node. When we talk about a node, the concept of a node in the circuitry, it simply means they all connect to the same conductor, the same chunk of conductor, the same chunk of copper on the circuit board. Okay. Are we still good with this discussion? All right, very good. So what does that mean? Okay, so as a result, okay, because we are changing or we are determining at least one of the input of n1, so now after a certain time delay, we want to see if we can tell what N1 is going to output, and we want to see what N2 is going to output. Now, sometimes, okay, you cannot tell. Okay, sometimes there's just not enough information based on the known state of the input to determine the output of a gate. But in this case, we do have enough information because these both N1 and N2 are NAND gates, which means if at least one input pin is a 0, the output is going to be a 1. In both cases, in both the case of N1 and N2, we do know that at least one input pin is a 0 at this point. So now we know both of them are going to output 1s. But then we also know where the output of N1 and N2 are connected to, because now we can also say SR.S is a 1, SR.R is also going to be a 1, because the nodes are connected here, because you can see from the diagram how the output of N1 is connected by a conductor to the input S of the SR latch, and N2 connects to R of the SR latch. So that part is instantaneous, and that's why they got lumped together into one single block of analysis. And now we know the state of the SR latch. Now we are not going to go through the analysis that we did on Tuesday and the earlier part of today, because now we look at the SR latch as one single component. It is not a gate, okay? And SR latch is not a gate, but nonetheless, it is a component where we understand the behavior. So what we're going to do next is we say, well, now that we know both inputs of the SR latch are 1s, we just know the SR latch is Q and NQ are maintained. Okay? We cannot really tell at this point. There's no way for me to tell whether Q is a 1 or 0 and whether NQ is a 1 or 0. There's no way I can actually tell what the state is, but I know it is maintained. That's all I can say. Is that okay? All right. So the next thing we want to do is to say, well, what if En is a 1? And now once En is a 1, it is important to understand, to know what D is, because it's supposed to enable the changing of Q of the SR latch to mirror whatever D is. Okay, so that becomes kind of important. So I'm going to analyze that on the next slide, and we're just going to make a copy of this circuit first, and then paste it onto the next page like that. And now we can say we're going to change En to a 1, and we're going to change D to a 1 too. Okay, now you can change D to a 0. The analysis is slightly different, but it's going to be very similar to when D is a 1. But we do want to kind of go through this propagation of changes, so that we can find out what's going to happen to this circuit. All right. So the first thing we know is just using the conductors. So we now know that N1 in 0 is going to be a 1, and because this is now a 1, and this is also a 1, we also know that N1.in bracket 1, the second input, is also going to be a 1. As far as N2 is concerned, we know N2.in bracket 0 is going to be a 1, and N.in is going to be a 1. So these are all the things that we know right now. Now somebody may say, but the output of N is going to be a 0. Not yet, okay? Because that also takes a propagational delay. So this one thing here, this entire block, is instantaneous. The moment we change En and D both to 1s, these are the things that we can conclude like right away. So after a certain delta amount of time, which is the propagational delay, now we can look at the gates and also the devices where they saw a change of input, and then we can try to determine what those things are going to output. Okay, so we look at N1 and we ask the question, can we tell what N1 is going to output at this point? The answer is yes, because both input pins of N1 are 1s. not only are they known, they're both ones, so we know n1 is going to output a 0 at this point. So n1.out is going to be a 0, and depending on where it is connected to, which is sr.s, that is also going to be a 0. So sr.s is also going to be a 0. What about the other stuff? Okay, we look at n2, and unfortunately for n2, we cannot quite decide what n2 is going to output, because the only thing we know from before is the first input of n2 is a 1. We just know that this pin of n2 is seeing a 1. We don't know what this pin is seeing at this point of time. On the other hand, we do know what the output of n, which is the NOT gate, is going to output at this point of time. So we're going to say n.out is a 0 at this point, because the input of n, the NOT gate, is a 1. So at this time, we know the output of n is going to be a 1, which also means we also know that we are changing n2 dot in bracket 1 to also be a 0. Okay. So Daniel is asking, are we just seeing what happens when we change the inputs, or is there an overall point we are looking for? So we are looking for a point when everything settles, okay, that there are no more changes being propagated. But at this point, we are taking into consideration that there's a time lag between the changes of the input of a gate or a device like the SR latch and the changes of its output. So we're taking into consideration. So now we got one block like this, okay? After a certain amount of time, n2 is going to respond to the changes of its input, or in this case it is the second pin of n2 having a known state after a certain delta. So after a delta amount of time, the first thing we notice is, hey, now we know what n2 is going to output. One input is a 1, the other one is a 0, so n2 is going to output a 1. So now we know n2.out is a 1. What about the SR latch? Well, all we know is SR.R is also going to be a 1 at this point, because the output of n2 is connected to R of SR, is connected by a wire or by a node, so that change is instantaneous. But that's all we can tell at this particular time, because we don't know what the SR latch is going to do at this point. Okay, so we block this, and then we say after a delay. So once the SR latch is having both of its inputs determined, S is a 0 and R is going to be a 1, it is only up to this point that we know R is going to be a 1. So now, only now, we can determine what the output of SR is going to be. So now we can say SR.Q is going to be a 1, SR.NQ is going to be a 0. And as a result, the output of the entire circuit itself, Q is going to be a 1, and Q is going to be a 0. And that is the final block, because we don't have anything that goes back to an earlier component in this particular circuitry. So the analysis or the change of the propagation of change only goes in one direction, which makes this particular circuit a little bit easier to analyze. All right. So the bottom line is the circuit doing what I said the circuit should be doing? So to answer that question, the first thing you need to know is to remember what I said about what this circuit is supposed to do. When En is a 1, Q is supposed to mirror what D is. Is that done at this point? Exactly. Okay, so very good. So as an exercise, okay, I'm not going to do it here, but as an exercise, I want you guys to basically just change the state of D. Instead of a 1, change it to a 0. And then see how the changes are being propagated. So it would be a good exercise, because you'll be following about the same steps, but not exactly the same. So I think that would be a good exercise. It's not going to be graded. It's just going to be a suggested activity to help you understand this circuitry. All right. Any questions about the D flip-flop at this point? No questions. All right. So if there are no questions, we're going to move on to another D flip-flop, but this one is called edge-sensitive D flip-flop. So this is in section 5 now. And once again, we have the circuitry specified in a kind of obscure way because it's all in text. So of the remaining time, okay, I think we can still draw the picture first, but we may not have enough time to go through the following of the propagation of changes for one particular cycle. So I'm gonna at least draw the picture first, and then we'll go ahead and analyze this on next Tuesday. But I would highly recommend all of you to read the text description here, because basically what you're seeing with these stuff here, that's just me doing the analysis of propagation of change. Instead of using a picture, it's using text. Alright, so let's go ahead and take a look at the circuitry. So once again, we have a clock this time. So it's not a enable anymore. This time it is a clock. And we also have a data pin, which is basically the same thing as the D pin from before. Oh, you cannot see the tablet. There we go. Okay, so these are the inputs. And then for the outputs, we have just a single pin Q. Okay, so I'm going to put Q all the way on this side because this is a slightly more complex circuit, so I want to leave myself enough room in between. And to the placement of the components, I want things that are connected to clock and data to be more on the left hand side, and things that directly output to Q to be more on the right hand side. That's just common sense, right? If you don't want your picture to look too ugly, this is how we do it. So now we want to know what clock and data are connected to as the first level. So we can see this node is connecting the data pin to N2, and we know that the clock is connected to N1, so we got N1 and N2. Now this time N1 and N2 are different. One has 3 inputs and the other one only has 2 inputs, so they are not exactly the same kind of NAND gate. Okay. All right. So one thing at a time. The data pin connects to the second input of N2, and the N2 only has 2 inputs. Okay. So let's get to the picture. And so we have N2 being here, and the data pin connects to the second input of N2. So this one is taken care of. And then the clock pin goes to the second or the middle pin of N1, because N1 is the one that has 3 inputs. So we're going to draw a slightly larger NAND gate here. And clock goes straight into the middle, which is the second input of N1, like that. But it also connects to S.R, and now we want to look at how the 2 SR latches S and C are utilized. So we can see C.Q goes to the Q pin, so it only makes sense for the SR latch C to be placed here. And with every SR latch, it has SR as input, Q and NQ as output. But in this case, only the Q output is connected. The NQ output is just dangling. It's perfectly okay to have output pins dangling and not connected to anything, but it's not so okay for input pins to be dangling. All right, so now we need to find out how R is used. SR latch S is used, because we want to find out where should we place the SR latch S. So S.R connects to the clock pin, and then S.S connects to here. So there's we can just put it right about here. Maybe about here. So this is SR latch S. It has its own input S, its own input R, output N, Q, and output NQ. And then we want to connect the clock pin to S.R. Okay, so the clock pin connects to S.R like so. Alright, moving on, we have the output of the NAND gate, N2, connected to the third input pin of the input of N1. So N2 goes back to N1. So this is N2. It goes back to the third input pin of N1 over here. But there's also the same conductor is also connecting to S.S. So S.S is over here. And you can kind of see how this is a little bit on the ugly side. We can clean this up and make it look nice later. But right now we just want to figure out the connectivities. Oh yeah, I can definitely do that. I'll do even better. I'll turn it off. There we go. And then we look at the output of N1. It goes to the first pin of N2. So this one goes all the way back to here. But it also has to go to C.R. Okay, so C.R is here. All the way over there. Oh, okay. You cannot see the picture, can you? There you go. So here's the picture. And now we have S.NQ goes to the first input of N1. So I'm going to do it on the tablet first because otherwise I cannot remember, how things are connected. So S.NQ goes to the first input of N1. Oh, this is going to look ugly, but that's okay. We just want it to be functional. And it also connects to C.S. So C.S is over here. Okay, so now I can show the picture because when I was drawing, I cannot remember how things are connected and draw at the same time. So this is what we have after we connect basically this particular node from the output S.NQ. It also connects to C.S. And we C. Yep, that's this one, and then we have this one here. So I think we got everything connected. Okay, so now we want to double check, right? So to double check, this one is not foolproof, but it is a good way to double check, is to make sure that the input pins of every single component is connected to. That is one general rule that we have to make sure. So in this case, N1 is a 3-input NAND gate. All 3 inputs are connected. N2 is a 2-input NAND gate. Both inputs are connected. S is a SR latch. Both inputs are connected. Now, even though output Q is not connected to anywhere, that's okay. No, as I said a little bit earlier, it is perfectly okay for an output pin of a particular device not to be connected. It's kind of like when you write a C program or C++ program, it's okay to ignore the return value of a function. It's not a problem. But when it comes to the input pins or the parameters of a function, it's probably a very bad idea to not specify one of the parameters. Okay. Now C++ won't let you do it, because it will actually count the number of parameters. But if it could, it would be a terrible idea not to specify one of the parameters. So it's the same thing with the circuit. C is an SR latch. It has 2 input pins, which are S and R. So everything checks out at this point, and we are out of time. So this is where we're gonna end today's lecture. There are no new labs today, so you are basically just continuing to finish up your positive exponent program, which is due on next Tuesday at 9 a.m. Other than that, no new activity to do other than the suggested activity from earlier. Basically, looking at this diagram, instead of making d equals to 1, make d equals to 0, and see how Q is going to mirror the state of D when En is a 1. So that would be a suggested activity. Daniel is asking, can I fit the circuit and the description in the same window? Going to screenshot them side by side. Which diagram? Are you talking about the edge-sensitive D flip-flop or just the D flip-flop? I'm gonna guess it's the D flip-flop. I mean the edge-sensitive D flip-flop. I could be wrong. Daniel? Which circuit are you referring to? You can always screenshot and then place the components any way you want. So I'm not seeing any reply from Daniel, so I'm just gonna show it here. And possibly scroll this stuff up like that so you can see both the description and the circuitry. Is that what you want? Not quite side by side, but top down, But I think that's the same thing, right? Okay, excellent. You're welcome. All right, so I'm gonna stop the screen share. I'll still be online in case anyone has any question about the positive exponent program. Other than that, there's no new lab today. All right. Well, you guys have a nice weekend, and I'll see you guys next Tuesday. But please read ahead of me because this particular module has a few more tricks down the line, so you gotta read a little bit more. And just the edge-sensitive D flip-flop takes a little bit of time to analyze too, so you're gonna need a little bit of time to read that first. All right, cool. Okay, so have a nice weekend, and don't forget to turn in your positive exponent program, and I'll see you all on next Tuesday.